The Dining Philosopher's Problem. The Dining Philosopher's Problem is the classical problem of synchronization, which says that five philosophers are sitting around a circular table, and their job is to think and eat alternatively. A bowl of noodles is placed at the center of the table along with the five chopsticks for each of the philosophers. To eat, a philosopher needs both the right and a left chopstick. A philosopher can only eat if both immediate left and right chopsticks of the philosopher is available. In case if both immediate left and right chopsticks of the philosopher are not available, then the philosopher puts down their either left or right chopsticks and start eating again. The dining philosopher demonstrates a large class of concurrency control problems, hence it's a classic synchronization problem. So this is the figure, the five philosophers sitting around the table. Let's understand the dining philosopher's problem. With the below code, we have used figure 1 as a reference to make you understand the problem exactly. The five philosophers are represented as P0, P1, P2, P3, and P4, and five chopsticks by C0, C1, C2, C3, and C4. So this is the code. Suppose philosopher P0 wants to eat. It will enter in philosopher function and execute take chopsticks. By doing this, it holds C0 chopsticks. After that, it executes take chopsticks I plus 1. By doing this, it holds C1 chopsticks since I is equal to 0. Therefore, 0 plus 1 ampere pipe is equals to 1. Similarly, suppose now philosopher P1 wants to eat, it will enter in philosopher function and execute take chopsticks. By doing this, it holds C1 chopsticks. After that, it executes take chopstick. By doing this, it holds C2 chopsticks since I is equals to 1. Therefore, 1 plus 1 percentage pipe equals 2. But practically, chopstick C1 is not available as it has already been taken by philosopher P0. Hence, the above code generates problems and produces race conditions. The solution of dining philosopher's problem. We use a semaphore to represent a chopsticks, and this truly acts as a solution of dining philosopher's problem. Weight and signal operations will be used for the solution of the dining philosopher's problem. For a picking of chopsticks, weight operation can be executed, while for releasing a chopstick signal, semaphore can be executed. What is semaphore? Semaphore is an integer variable in S that, apart from initialization, is accessed by only two standard atomic operations, weight and signal, whose definitions are as follows. So this is the code. So from the above definition of weight, it is clear that if the value of S is less than or equal 0, then it will enter into an infinite loop because of the semicolon after while loop. Whereas the job of the signal is to increment the value of S. The structure of the chopstick is an array of semaphore which is represented as shown below. So this is the semaphore C5. Initially, each element of the semaphore C0, C1, C2, C3, and C4 are initialized to 1 as the chopsticks are on the table and not picked up by any of the philosophers. Let's modify the above code of the dining philosopher's problem by using semaphore operations, weight, and signal. The desired code looks like this. In the above code, first weight operation is performed on take chopsticks and take chopsticks I plus 1 percentage 5. This shows philosophers I have picked up the chopsticks from its left and right. The eating function is performed after that. On completion of eating by philosopher I, the signal operation is performed on take chopsticks and take chopsticks I plus 1 percentage 5. This shows that the philosopher I have eaten and put down both the left and right chopsticks. Finally, the philosopher starts thinking again. Let's understand how the above code is giving a solution to the dining philosopher problem. Let value of I is equals to 1, initial value. Suppose philosopher P0 wants to eat. It will enter in philosopher function and execute weight take chopstick C. By doing this, it holds C0 chopsticks and reduces semaphore C0 to 0. After that is execute weight take chopstick C I plus 1 percentage 5. By doing this, it holds C1 chopsticks since I is equals to 0, therefore 0 plus 1 percentage 5 equals 1, and reduces semaphore C1 to 0. Similarly, suppose now philosopher P1 wants to eat. It will enter in philosopher function and execute wait take chopsticks ci. By doing this, it will try to hold c1's chopsticks but will not be able to do that. Since the value of the semaphore c1 has already been set to 0 by philosopher p0, therefore it will enter into an infinite loop because of which philosopher p1 will not be able to pick chopstick c1, whereas if philosopher p2 wants to eat. It will enter in philosopher function and execute wait take chopsticks ci. By doing this, it holds c2 chopsticks and reduces and execute wait take chopsticks by it is hold t2 chopsticks and reduces semaphore c2 0 after that. It execute wait take chopsticks I plus 1% pi. By doing this, it holds c3 chopsticks since I is equals to, therefore 2 plus 1 percentage pi equals 3 and reduces semaphore c3 to 0. Hence, the above code is providing a solution to the dining philosopher problem. A philosopher can only eat if both immediate left and right chopsticks of the philosopher are available, else philosopher needs to wait. Also, at one go, two independent philosopher can eat simultaneously. For example, philosopher P0 and P2 and P1 and P3 and P2 and P4 can eat simultaneously as all are the independent processes and they are following the above constraint of dining philosopher problem. In the above code, first wait operation is performed on take chopsticks and take chopsticks I plus 1 percentage 5. This shows philosophers I have picked up the chopsticks from its left and right. The eating function is performed after that. On completion of eating by philosopher I, the signal operation is performed on take chopsticks and take chopsticks I plus 1 percentage 5. This shows that the philosopher I have eaten and put down both the left and right chopsticks. Finally, the philosopher starts thinking again. To avoid deadlock, some of the solutions as follows. Maximum numbers of philosophers on the table should not be more than 4 in this case. Chopstick C4 will be available for philosophers P3, so P3 will start eating and after that, the finish of his eating procedure, he will put down his both the chopsticks C3 and C4. For example, semaphore C3 and C4 will now be incremented to 1. Now philosopher P2, which as holding chopstick C2 will also have chopstick C3 available. Hence, similarly, he will put down his chopsticks after eating and enable other philosophers to eat. Next, a philosopher at an even position should pick the right chopsticks and then the left chopsticks, while a philosopher at an odd position should pick the left chopsticks and then the right chopsticks. Next, only in case if both the chopsticks left and right are available at the same time, only then a philosopher should be allowed to pick their chopsticks. And last, all the four starting philosophers P0, P1, P2, and P3 should pick the left chopsticks and then the right chopsticks. Whereas the last philosophers P4 should pick the right chopsticks and then the left chopsticks. This will force P4 to hold his right chopsticks first since the right chopsticks of P4 is 0, which is already held by the philosophers P0 and its value is set to 0. For example, C0 is already 0, because of which P4 will get trapped into an infinite loop and chopstick C4 remains vacant. Hence, philosopher P3 has both left C3 and right C4 chopsticks available. Therefore, it will start eating and will put down its both chopsticks once finishes and let others eat, which removes the problem of deadlock. The design of the problem must illustrate the challenges of avoiding deadlock. A deadlock state of a system is a state in which no progress of system is possible. Consider a proposal where each philosopher is instructed to behave as follows. The philosopher is instructed to think till the left fork is available. When it is available, hold it. Next, the philosopher is instructed to think till the right fork is available. When it is available, hold it. Next, the philosopher is instructed to eat when both forks are available. Then put the right fork down first, then put the left fork down next, and repeat from the beginning. That's all. Thank you.